Hello students, and welcome to the video lecture on Chemical Reaction Engineering 2. We are dealing with Unit 1-2 on catalysis and catalytic reactors. In the last lecture we have discussed on heterogeneous analysis for a reactor design, where we have seen there are multiple steps based on the experimental data which is available with us, which can be analyzed to get the rate law form, to derive the rate law parameters. Once you have all these parameters together, you can use it for the design of any reactors. Today we are going a step ahead, where we are going to discuss on deactivation of the catalyst. I've shared these notes with you, which are also extract from the book from Fogler. Now, deactivation is a very well-known fact that nothing is mortal in this universe, so does the catalyst. Any catalyst which we have discussed by for now, we have always made up a single assumption, that is the total active sites does not change with time, and that is where we have never discussed on deactivation. But what is the real scenario? Catalyst activity is usually lost during the course of reaction, and we usually quantify the same by calling it as activity of the catalyst, which is denoted as A of T. There are two categories when we talk about deactivation. One is separable kinetics, another is non-separable kinetics. When I say a separable kinetics, it actually means that the deactivation or activity of a catalyst can be separately studied, and the kinetics of a reaction can be studied. Now, these both are not coupled, and both of these can be studied independent of each other. That is where we call this as separable kinetics. It is very uncommon to have a separable kinetics, while it is very common to have a non-separable kinetics. What I mean is, the rate is always a function of activity of a catalyst and that of a fresh catalyst. When I say activity as a past history, I say that how the activity is going to work with time, that is already known as a separate part, and when you add a fresh catalyst, you will come to know the true intrinsic kinetics there. When these both are coupled, you don't know how the catalyst activity is going to behave in this reaction condition, and you cannot separate it from the kinetics. We call it to be non-separable. Now, this is all because there is a non-ideal surface, or deactivation always happens as a multi-step reaction and is dependent on the reaction conditions, which is at any instant of time. And that is where we define activity as a ratio of instantaneous rate to the rate of catalyst initially. Now, when you talk about initial rate, catalyst is fresh. So all the active sites are available for the reaction and there is no deactivation. So we call activity value to be 1 when the rate is at initial conditions. But as we move ahead with time, you see the activity will drop. Now, rate of disappearance of a reactor when I am talking of non-separable kinetics, in addition to the rate constant, which is function of temperature and the concentration of the species, it depends on the activity of the catalyst. As this is a coupled one, we have a rate of catalyst decay or deactivation rate as well. This A comes through dA by dt as a function of either A into Kd, this is rate constant. This is rate constant for deactivation or decay of catalyst. This is activity of catalyst and this is function of the species. Now, depending on the type of deactivation, few terms can move here or there. Now this activity we either take sometimes first order or second order decay. Most general it is taken as second order decay. Now this has been come through the experiences and the usage by for now. Let us try to discuss on the different types of deactivation. The very first type of deactivation is sintering or aging. Now when I say aging, that means over the age of catalyst it deactivates. So it is loss in the surface area of the active metals over the time. Point to be noted, it is by the prolonged exposure to the temperature. Over the period of time through the chemical reactions, there is a vast variation in the temperature and the pressure through the reactors, and this changes actually ages the catalyst. And what happens to this exposure of temperature is crystal agglomeration. What it means is you have a different active species that are being through the reactor that is there into the catalyst. Over the time they starts to move in through the pores and it forms a bigger agglomerate. Now this metal species are no more of the same size, same time there is no same activity as it would have given in the smaller size. Second thing, what an exposure to temperature causes, narrowing or closing of the pores inside the catalyst and a rupture of a structure. Now you may have a multiple active sites inside the pore of a catalyst. If at all due to certain pressure temperature changes, if this pore gets ruptured or if this gets narrowed, what happens is this will not be accessible on the right side. These active sites will no more be accessible and there will be a reduction to the total active metal which are available for reaction. Now this agglomeration or this rupture, this is called as sintering of catalyst or aging of catalyst. What do you think? It is dependent on temperature. So here no species of a reactant or a product is responsible for the deactivation. That is where we write the rate law for deactivation or decay law as we are taking it as second order Kd, that is deactivation constant, into A square, which is function of temperature, as minus dA by. If you separate the variables and integrate, you get A as 1 upon 1 plus Kd T. Integration is from t equal to 0 it is 1, and t equal to t it will be A. Now amount of centering, active surface area, you can simply multiply it with AT, so you get the change in the surface area as well. The deactivation constant also follows the Arrhenius law, where Kd at any point of time with initial you can have an exponential relation. Point is, how should we be able to reduce this centering or aging of a catalyst? It is very clean and clear that the metal or a rupture is happening because of temperature. So if you reduce this temperature, if you want to reduce this centering, you can reduce by about 0.3 or 0.4 times to the melting point of metal. You will be able to have a reduced centering. Let's move on to the next type of deactivation, which is called coking or fouling. It is a very common word for any petroleum engineer to call for coking an NFCC catalyst. Fouling is also a well-known word to us when we talk in terms of heat exchangers and things. What it means is making a layer of a deposition onto a surface. When I say deactivation by coking or fouling, it also means that the deposition of a certain carbonaceous material onto the surface of catalyst. It is very common with the hydrocarbon reactions, and what signifies is the amount of carbonaceous material that has occupied the catalyst surface. So there is an equation which is given for the amount of coke which is formed over the surface in due time. It is given by Cc, that is amount of carbon, which is given in gram per meter square, plus A into T raised to power n, where parameter A and parameter n are the fouling parameters, which are in turn dependent upon the feed rate. Now, these expressions are given by the different companies with their experiences on dealing with coking and finding out these parameters. East Texas oil field has given that the percentage of coke can directly find out. It simply multiply 0.47 with the root of time to which it has been exposed. Another form for activity of a catalyst is given by 1 upon rate constant of coke formation into amount of coke raised to power p plus 1. If you sort this out using our previous expression of amount of coke and try to accumulate the constants, what you end up as 1 plus k dash t raised to power m. So previously we had looked after deactivation by centering, now we are looking for deactivation by coking. The activity is given as 1 upon 1 plus k dash t raised to power m. Now these two constants are also being given based on the experiences with the different feeds. And this decay law has been given as 1 upon 1 plus 7.6 t raised to power half. This is one of the expression which is given by the Texas oil fields. There are other forms which are available by the different people who are dealing with those hydrocarbons. In this case, K dash is 7.6 and M value is 1 by 2. Other forms of this are also available, which are dependent on amount of carbon that is deposited over time. Now, any of these expressions we can use. What did we learn in coking is amount of coke formation is directly dependent on time, and activity of a catalyst is dependent on those following parameters, and one of the dominant parameters is amount of coke. So overall, if you know the coke formation and the following parameters, you will be able to find out the loss in activity of a catalyst due to coking. One of the important things to be noted here is this is irreversible deactivation. What I mean is, if you can remove this coke by regenerating or oxidizing using another reactor, your catalyst can be reused. These depositions can be permanent or it can be removable. For coke, yes, these are mostly reversible, where you can remove coke by oxidizing it and reusing the catalyst. While in the case of sintering or aging, these are irreversible, where the metal particles you cannot redistribute in the surface area. At the same time, you cannot reconstruct the pore structures. Let us move on to the next part of this. We're just trying to combine and see how to derive an equation of conversion when you have a batch reactor with a catalyst decay. Now till now we have seen the rate equations where we have dealt only with the kinetics, but if you have a non-separable kinetics, that is where you need both the things to be clubbed, and we see how this rate expression for a simple batch reactor first order reaction changes. We are considering a first order reaction A gives B with a second order of decay law, that is minus d by dt is kd. We wish to find out the equation for conversion. Our normal equation for conversion is minus ln 1 minus xa equals kt. Now here if you say, now the rate equation is dependent on activity of a catalyst. And previously we have seen this equation number 1, where we have shifted the variables and integrated it to get a of t as 1 upon 1 plus k dt. Now Ra is Ca0 dxa by dt, k dash, Ca becomes Ca0 1 minus x, and A becomes 1 upon 1 plus k dt. Now solving this expression, you get is minus ln 1 minus xa, k dash upon, when you integrate this with respect to time, you get ln of 1 plus k dt. So our simple expression of minus ln 1 minus xa equal to kt has now changed because of deactivation. Space k dash upon kd ln of 1 plus kd into t. Is it clear? So this is the final rate expressions. So this brief lecture, what we tried to understand today, let us go back to the start and see what we have studied today. We studied the deactivation of catalysts. We tried to understand what are the factors that cause the deactivation. We have studied the difference in the separable and non-separable kinetics. We talked on the activity of catalyst, the dependence on the three different factors. One is depends on time, temperature, and the species. We have dealt with the two different types of deactivation. One was centering and aging, where you have agglomerations and rupture of pores, basically reduction into the surface area. We see also about the coking and fouling as the second deactivation, which is predominantly on the amount of coke, tenacious material that falls onto the surface of the catalyst. We have seen the activity expression for coking as well, and we have to derive a simple change in the conversion expression that happens because of deactivation of catalyst. Now, moving ahead, I have a simple gloss. What are the different forms of carbon that you can find out? Does all form of carbon are possible to be removed? What kind of carbons will be able to delete? So with this, I end today's lecture, and we'll continue with the deactivation in the next lecture as well. Thank you.